We are discussing the concept of hybridization, right? And we wanted to know what is the basis, why did we introduce the theory of hybridization? I was always mentioning to you. The reason why we introduced hybridization is because there were serious flaws in the valence bond theory. One of the biggest merit of valence bond theory remains, and we will take it forward whenever you deal things in chemistry, that is the concept of overlapping, right? We are asking questions in covalent bond, where is the strength of the covalent bond will be coming from? If you don't introduce the concept of overlapping, I think there is no theory which is so convincing except for the concept of overlapping introduced by what? Valence bond theory. Otherwise, we would have not explained the strength of the covalent bond, where is it derived from. It's not the case of ionic bond where you have a cation and an anion, you have your electrostatic force of attraction, and the bond is very much convincingly, and the strength is obtained by this electrostatic force of attraction. That thing is missing in covalent bond. So the concept of overlapping is one of the biggest merits of what? Valence bond theory proposed by Linus Pauling. Right? And if you consider one more merit, I think if there is anyone who's beautifully explained, very beautifully explained diatomic molecules like hydrogen, fluorine, chlorine, oxygen, nitrogen, HCl, HF, these are all diatomic molecules, meaning these molecules will exclusively have two atoms. And if there is anyone who can beautifully explain, right, the formations of these diatomic molecules, it would be, the credit would be exclusively for Linus Pauling, where he introduced the concept of overlapping, right? That is where the celebration is. But if you actually see the other side, when you get into a polyatomic molecules, that is more than two atoms, that is, you can consider ammonia, water, H2S, H2Se, H2Te, right, whatever, these triatomic molecules or even polyatomic molecules, I think there are serious flaws in it, and he is not in a position to explain any of these bond angles in these polyatomic molecules. You must understand this, right? For example, he cannot explain the bond angles of ammonia to be 107. He cannot explain the bond angles of methane to be 109 degrees 28 minutes. He cannot explain sulfate ion, which has 109 degrees 28 minutes, or whatever. Except for the diatomic molecules, he has beautifully explained. And the only key takeaway from the valence bond theory is, of course, what? The concept of overlapping. Even we proceed to hybridization, the concept of overlapping will prevail. Why it prevails? Because what happens is, if two atomic orbitals are overlapping, you get a larger volume to revolve around. So when the electrons get and delocalized over a larger volume, I think you're losing more energy. When you lose more energy, I think the energy is lost, and the stability and energy are inversely related, you must understand. So the concept of overlapping is the biggest merit of what? The valence bond theory, you must understand that, right? Now coming to the serious flaws, why, if you wanted to understand hybridization, which I was telling in previous sessions, right, if you wanted to understand hybridization, you should know the necessity why we actually proposed this. The necessity being, you have a serious flaws in this fellow's valence bond theory proposed by Pauling. One of the serious flaws is the p vector onto the s is absolutely not fixed. When the p orbital is projected onto the s orbital, the direction in which the overlapping is happening is absolutely not fixed, whether it's acute, obtuse, or whatever. Right, 70 degrees, 60 degrees, this is not fixed. That too at the 11th hour, the moment you're overlapping, then you're thinking of, which direction you need to come and all these things. So this is a serious flaw where you don't have the direction of the P onto S, then the bond angles are absolutely not fixed, and the structures are not determined, and all these things will be considered to be absolute demerits. The second thing is, whenever p orbitals are involved, which are mutually perpendicular, then I think the bond angle remaining to be 90 is clearly suggesting that you take any polyatomic molecule like ammonia, water, H2S, all the bond angle remain to be what? 90 is ridiculous, silly, and absolute nonsense, right? So these two actually form the basis for the hybridization, you must understand. Now, what is the burning thing here in hybridization is, what is the greatest necessity here is basically, right, before participating in bonding itself, if things are fixed, right, the bond angles are fixed, the structures are fixed, then it would be a great idea. You must understand that. That's what exactly happens in hybridization. Remember, hybridization is basically not a method of preparations for molecules. These molecules are already there, the bond angles are fixed, everything is fixed. We need to have a convincing theory which backs that bond angles, which backs the structures of these molecules, you must understand. So when we started off hybridization, it's basically like this. Number one, it happens before bonding. It happens before bonding, and it happens within the atom, and it is intermixing of atomic orbitals within the atom before bonding in excited state to generate entirely a new set of orbitals, which are called hybrid orbitals, which have better directional properties. Better directional properties than what? Atomic orbitals, right? So this nuisance of which way to come, what angle to come for the overlapping, and all these discussions just at the nick of the moment have been completely ruled out. Now what is happening is, before you call your partner for the bonding, the atom that is called, we refer it to be a central atom in which the atomic orbitals are intermixing with one another and generating entirely a new set of orbitals, and that orbitals are said to be hybrid orbitals, which possess what? Better directional properties. Meaning, simply before bonding, the bond angle is fixed and the structure is fixed. The only thing which is left out is basically the overlapping, right? That is the first thing. Second thing is, you understand you have several types of hybridization. I've been writing all these days. And remember, to judge the hybridization, we have a formula, H is equal to half into V plus M minus C plus A. Using that, we can actually determine what? The hybridization, because it gives you the number of hybrid orbitals. And you refer, if the number of hybrid orbitals are basically 2, it is basically sp. If it is 3, it is basically sp2. 4, it is sp3. And remember, it is 5, it is sp3d. And it is 6, it is sp3d square. And it is 7, which is sp3d cube. You must understand this. That is how, if you know the H value, that is the number of hybrid orbitals, then you are in a position to fix the hybridization of any compound given to you. You must understand. And the most critical thing, I was telling you in the exam, you'll be asking number of pi dp bonds and pi bp bonds that I was explaining in the last session. You must understand that is one of the questions, right? So what is happening here? Basically what is happening is, even though we are proceeding with the hybridization, and we have covered most number of polyatomic molecules which were not covered by valence bond theory. I draw the attention of everyone here. So very few molecules were covered in the valence bond theory, and we are excited. We have proposed what? Hybridization, great theory, great convincing theory, and we have covered some more molecules, right? But the issue happens is, what happens is, even hybridization has some flaws. Hybridization also could not explain some of the molecules. It cannot, because it has ignored something. As I said, everyone has merits or not, we do not know, but one thing is for sure, that they will be having some demerits. You must understand, right? So in the case of hybridization, which is a hypothetical theory, we were able to cater to some of the molecules to determine the bond angles, to determine the structures and all these things. But coming to some molecules, I think the hybridization also fails. Not only fails, it miserably fails, but because it ignores something. That's what we will be taking up now. Observe carefully here, right? So I'm basically telling you why the textbook is fat. The textbook is fat because every theory you propose will be having some flaws, right? So that flaws are taken up for correction, and the textbook goes on what? Swelling. That's how it is. We started off with what? Covalent bond. We said valence bond theory has flaws, and to correct that we proposed what? Hybridization. And then now I'm basically telling you that hybridization cannot cover all the molecules that are outside. You must understand, because you ignored a critical thing. You basically ignored a critical thing, and then you face issues. Like, for example, look into this, what hybridization cannot cover, and then I propose another theory to you. Watch carefully here. Watch what is happening here. Watch. Let's take the case, flaws in hybridization, right? Hybridization cannot explain all structures. It cannot explain all the structures or all the molecules that are available. Let's take an example and check it out. What did he ignore about that? He has ignored something, and we wanted to fix that, and we will arrive at that taking an example. What's this? Take the case of ammonia. Take the case of ammonia. Let's actually write the draft. Nitrogen is 7. It's 1s2. 2s2, 2px1, 2py1, and 2pZ1. This is the nitrogen configuration. That's a nitrogen configuration. So what we will do first of all, what type of hybridization is taking place in ammonia? Let's use the formula for it. If I use the formula for it, let's take H is equal to half into V plus M minus C plus A. That is a formula to determine what? The hybridization in the central atom nitrogen in ammonia. And if I can do this, then H is equal to half into V is the number of valence electrons. V is the number of valence electrons. If the number of valence electrons is also called group number. It is also called group number. So understand that then the group number of nitrogen is 5. Nitrogen belongs to 5th group. Carbon belongs to 4th. Nitrogen belongs to 5th. Oxygen belongs to 6th. And halogens belong to the 7th group. You must understand, right? So if you write V, the group number of nitrogen is 5 plus M is number of monovalent atoms that are attached to the nitrogen. If you look into the number of monovalent atoms attached to the nitrogen, it is nothing but the number of hydrogens or number of halogens. Monovalent atoms in chemistry are only 2. It is hydrogens or halogens. That's all. There are only 2 types of monovalent atoms available in chemistry. That is hydrogens and what? Halogens. And if you look into this in ammonia, we are trying to find out this, right? So nitrogen belongs to 5th group and the number of hydrogens attached to nitrogen are 3. Right? And you look here, you don't have any cation. It's a neutral molecule. So no charge on the cation, no charge on the anion. It's 5 plus 3 by 2, which is 4. And 4 is basically sp3. If H value is 4, it is basically sp3. So if you look into this, this is the configuration. And if I can start the draft for it as usual, what we're doing, then I would like to write in ammonia, the central atom nitrogen, in ammonia, the central atom, which is what? Nitrogen, undergoes sp3 hybridization. It undergoes sp3 hybridization. It undergoes what? An sp3 hybridization. How do I know? This is the formula. You fix it off in the beginning itself. It is undergoing sp3 hybridization. So if I can write the formula for it, the configuration for it, then I write the electronic configuration of nitrogen. If you see, it is 7. So it is 1s2, 2s2, 2px1, 2py1, and 2pz1. And this is the outermost shell which I wanted to underline. That is the electronic configuration of nitrogen, right? Then let's go in for the hybridization now. The hybridization is basically sp3. Let us put the hybrid lock now. If I can lock it, it says hybridization of 1s and 3 p's, giving you 4 sp3 hybrid orbitals. You should understand. It is 1s and 3 p's. They intermix before bonding within the atom in excited state, and then you get what? 4 sp3 hybrid orbitals, and each sp3 resembling 25% of s character and 75% of what? P character, and all the 4 are sitting in a position. You must understand that, right? So if I can put the lock for you, this is the lock. 1s and 3 p's all involve in hybridization, and they generate 4 sp3s. And if I can draw the 4 sp3s for you, it looks like this. 1, 2, 3, and 4. This is basically an sp3. This is also sp3. This is also sp3. This is also sp3. You must understand that, right? So those are the 4 sp3s. And look into the lock. Look into the lock. How many electrons are involved in this lock? This is the lock of hybrid lock, because it is 1s and 3 p's. So it is 2 plus 1, 3, 3 plus 1, 4 plus 1, 5. So you have 5 electrons that are involved in the lock, in the hybridization, right? Let us distribute that. If I distribute 1, 1, initially 1, 2, 3, 4, and this is the 5. all the 5 have been distributed in all the sp3 hybrid orbitals. You must understand. Now let us draw the structure. Now I'm ready basically. I'm ready. I'm calling my partner now, the hydrogen, right? Come, overlap with me. If that is the case, then you have 4 sp3s. Look here, 1, 2, and 3. And here is one sp3. Here is another sp3. Here is another sp3. Here is another sp3. This is what all the 4 sp3s are. And you can distribute all the 5 electrons. It is 1, 2, 3, 4, and 5. So those are the 5 electrons. That is how the sp3 hybridization looks like. Now I'm ready. Now I'm ready. You have 3 unpaired electrons. Now I'm calling all the hydrogens to come and overlap with me. Ammonia has 3 hydrogens. So all of them are coming. And here is the hydrogen with the s orbital. And this is sp3 and this is s. This is sp3 and this is s. So I write sp3 and s sigma. It is a head-on overlap. So it's a sigma bond. Similarly, you take this will be again sp3 s sigma. So this is also right sp3 s sigma. And this is all the three hydrogens are what? 3 hydrogens are exhausted. That is how the ammonia molecule is formed. When we actually get through all this, when we go through all this, we find that absolutely what an explanation given by what? Hybridization for ammonia, because this is what we are doing for all other molecules. Right? What did we do? We just said ammonia's central atom is undergoing sp3. We have written the configuration. We have gone in for the hybridization, and the hybrid orbitals are sitting in a position. Then I called my partner, and here are the overlappings, and the ammonia molecule is formed. And the ammonia molecule is formed. This is what it is. This is the swift way. Now I draw the attention of everyone. Please understand, if this is the case, then understand that, then if this is the case, then understand that when it is sp3, when it is basically sp3, we expect bond angle 109 degrees. So bond angle basically we expect a bond angle, right? We expect a bond angle which is 109 degrees 28 minutes. And the shape must be what? Tetrahedral. You must understand. And the shape must be what? Tetrahedral. This is what we were told about sp3 hybridization. Whenever any central atom is undergoing sp3, all the 4 sp3 hybrid orbitals will be sitting in the corners of a tetrahedron, and the bond angle will be 109 degrees 28 minutes. This is what hybridization tells as far as sp3 is concerned. So even it is same for ammonia. Even it must be same for ammonia. That's what we have done. So the expected bond angle should be 109 degrees 28 minutes. But what happens is, if you look into the real bond angle, or we call this to be observed bond angle, it is basically 107 degrees. It's 107 degrees. And the expected shape is basically tetrahedral, but actually the shape also seemed to be absolutely pyramidal. It's pyramidal. So the shape got distorted, the bond angle got distorted or deviated from 109 degrees 28 minutes to 107, and the hybridization cannot explain this. You cannot explain this. You cannot explain the bond angle in ammonia, which is equal to 107 degrees, and the hybridization cannot explain at all. They can't explain. So what shall we do? Now we start searching for another theory. Right? Now let us understand. You wanted to ask me a question rather. Why is that happening? Why is this happening is an issue. Why is this happening is an issue, right? But before I tell why is this happening, let's take one more example. Then I think we'll get into it. Now look into this. This is a swift draft what I have written, which is a normal draft written for others. other molecules. This draft is common. What is a draft? In ammonia, the central atom nitrogen is undergoing sp3 and the ESC of nitrogen is this. And we went on for hybridization because that is the procedure. And after hybridization, I'm sitting in positions. Then I called the partners for overlapping and everything was fine, going well. So the bond angle was also fixed, 109 degrees, 28 minutes. But someone says that experimental bond angle in ammonia or the observed bond angle or the real bond angle in ammonia is 107 degrees. And the shape is not tetrahedral, but rather it got distorted to pyramidal. Why? There are absolute no answers. Well, we wanted to know why. We wanted to know why. But let us take another example and then fix this flaw. Right? Let's take another example. Look into this. Let's take another example. Then we will fix it off why such a thing should happen. Watch. Drawbacks. This is what we are discussing. Drawbacks of hybridization. Drawbacks of hybridization. Let's take the case of water molecule now. Let's take the case of water molecule, a simple water molecule, right? Let's actually check out what is hybridization in it. So I'll use the formula H is equal to half into V plus M minus C plus A, right? That is a formula. Let's apply to it. So this will be equal to half into V is the number of valence electrons. Number of valence electrons is otherwise group number. It is otherwise group number, and oxygen group number is 6th because oxygen belongs to 6th group. So if you write its configuration, it will be having 6 electrons in its outermost shell. 6 electrons in the outermost shell. That's nothing but what? Group number. So it is valency, so valence electrons are 6. And let us check out the number of monovalent atoms in water. In water, this is the central atom. This belongs to 6th group. And the number of monovalent atoms are hydrogens, which are 2. It's not a cation. It's not an anion. It doesn't have a charge at all. So it is again 8 by 2, which is 4, which is sp3. So I can simply say in water molecules, the oxygen is basically undergoing what? The sp3 hybridization. The sp3 hybridization, you must understand, right? So start the draft. Let's start the draft. That is our procedure. In water, the central atom, oxygen, undergoes sp3 hybridization. It undergoes what? sp3 hybridization. The central atom oxygen undergoes what? sp3 hybridization. That's fixed because in advance. Let us write the configuration now. So the ESC of oxygen, the excited state configuration of oxygen is basically 1s2 of oxygen, right? Of oxygen, which is 8. Right, it is 1s2, 2s2, 2px2, 2py1 and 2pz1. And as a chemist, I always have the habit of underlining the outermost orbit. So I underline this, right? So I'm underlining this. And you say the hybridization is sp3. So let us lock it. So if you lock it, if it is sp3, so it is 1s and 3p's, 1s and 3p's, 1s and 3p's. And this I lock it. This is the hybrid lock. That is a hybrid lock. It's 1s and 3p's. That's what water is. In water, the oxygen is undergoing sp3 hybridization. So that's what is the hybrid lock is. Now, I can write this what I've done. So 1s, and again it is 3p's, giving you 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals. And I can say the expected bond angle again 109 degrees 28 minutes, and then the shape expected must be what? Tetrahedral. This is what is fixed in advance. 1s and 3p's will undergo hybridization and you generate 4 sp3 hybrid orbitals, and all the 4 sp3 hybrid orbitals, if I can draw it here for you, this is how they look like. 1, 2, and 3 and 4. This is sp3, sp3, sp3 and sp3. All the sp3 belong to what? Oxygen, because it is the oxygen which is undergoing what? sp3 hybridization. That is what we refer it to be a central atom, right? So if this is the case, look into the lock. The lock will be having 4, 5, 6. So you have 6 electrons. 1, 2, 3, 4, 5 and 6. So total you have what? 6 electrons here. And you have 2 unpaired electrons. Similarly, if I can give you the diagram, then I think you have sp3s. This is one sp3. This is another sp3. And this is another sp3. And this is another sp3. You must understand, you have 4 sp3 hybrid orbitals. 1, 2, 3 and 4. These are all sp3s. They are not p orbitals. They look like p, because they have 75% p character and 25% what? S character. P orbitals are slim and trim. You can actually see the sp3 is a little bit fat because the s orbital has been mixed into p. So these are the 4, and now I distribute 4 plus 2, 6 electrons here. So start off 1, 2, 3, 4, 5 and 6. That is how the hybrid orbitals. I am now ready. Now I am ready. Call out the partners. The partners are hydrogens. The 2 hydrogens. So what I will do, these 2 are the hydrogens. And I think they will overlap here, and this is what is called sp3s sigma. sp3 of oxygen, S of hydrogen. Similarly, one more here. This is sp3s sigma. You must understand the sp3 of oxygen and S of what? Hydrogen. You must understand. In this shape, the expected bond angle is 109 degrees 28 minutes. But actually the real bond angle is basically for water, it is 104 degrees 36 minutes. Come on, man, this is 5 degrees deviated. This is ridiculous. This is 5 degrees deviation. And not only that, you can expect the expected shape. You have, see, the expected shape is basically tetrahedral. And the actual shape is basically angular. Come on, man, there is distortion in the shape, as well as you have the deviation from the normal tetravalency angle. That's nothing but what? 109 degrees 28 minutes have now become 104, which seem to be serious enough, because it's almost 5 degrees deviation, which cannot be discounted, and the hybridization cannot explain this, why there is a deviation from 109 toward 105, or the shape got distorted from tetrahedral to angular. These cannot be explained by hybridization. You must understand that, right? So how do we deal with it? There is something which we ignored while proposing the hybridization, hence we are struggling now, right? Hence we are struggling now. So you must understand. Well, I would like to give you a list of compounds, and the other list of compounds, there is something common in the first list which is not common in the second list. And the first list, the hybridization explains superbly. The other one, it fails. Let us actually see. Something has been ignored by the hybridization, but otherwise I think such deviations would not occur at all, right? Such deviations could not occur at all. I think while proposing the hybridization, something has been ignored. Definitely something has been ignored. And what is that which is ignored? We'll catch it up and we will fix it off. You must understand that. Shall we? So let us take one more example. Now, I'll give you a set of examples rather, not one. We'll have a volley of examples and compare with the other set of examples and check out what is missing in the first and the second ones, right? Then I think we'll fix it off what has been ignored in the concept of hybridization, which we were boasting that it is the best theory, right? Let us see. Watch carefully here. You know, hybridization best explains It best explains the following. It best explains the following. No one can explain better than hybridization than the following examples which I am about to write. Watch carefully here. Methane, it explains the best, right? And if you see BCl3 or BF3, the best, no one can explain beautifully than what hybridization concept explains these molecules, right? And then I have beryllium chloride, which the valence bond theory was struggling. The valence bond theory was struggling to explain beryllium chloride, where we were telling that the P projection onto S is absolutely not fixed, and he could not explain beryllium chloride, which now the hybridization is able to explain, right? Wonderfully they will explain, the hybridization will explain all these molecules. Even proceeding forward, right, this is basically undergoing sp3. These both will undergo sp2. This will undergo sp. And going back, then it is PCl5, which is sp3d. And SF6, which is sp3d2. And IF7, which is sp3d cube. You must understand. You have all these molecules, and opposite that, I think I have written the hybridization. Here, if you look into this, the expected bond angle, if I write, it is 109 degrees 28 minutes, right? And this one is 120 degrees. And this one is 180 degrees. And this one will have two set of bond angles, that is 120 and 90. And this one will have exclusively 90. And this one will have around 72 degrees. This is what is the bond angles, expected bond angles. Now you might ask me, what are the real bond angles or the observed bond angles? If I can write it for you, look into this. The observed bond angles. The observed bond angles. And they remain to be 109 degrees 28 minutes. And they remain to be 120, they remain to be 180, they remain to be 120, 90, and this is 90, and this is 72. There is absolutely no deviation. Look at this, there is absolutely no deviation. Absolutely no deviation. And even the shapes, if you look into this, the expected shape is basically for this is tetrahedral, and it remains to be tetrahedral. The second one is triangular planar, it remains to be triangular planar. This is linear, it remains to be linear. And this is trigonal bipyramidal, it remains to be trigonal bipyramidal. No distortions. Right, SF6, it is octahedral. Absolutely, the real structure is also octahedral. And if you look into IF7, it's pentagonal bipyramidal, and it remains to be pentagonal bipyramidal. So all the expected and the real bond angles are same, expected structures and real structures are same. There is absolutely no deviations at all. Now what is the issue? The issue is, I write the other set of things, observe. Now, I write the other set of things, observe carefully here. Observe here. Ammonia, pH3, water, H2S, sulfur dioxide. You take anything, these molecules. In these, you see the hybridization is sp3, 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 and sp2. You must understand. This one, H is equal to half into V plus M minus C plus A. Use this to find it out. For example, for this, that is half into 6 plus 0 minus 0 plus 0, it is 6 by 2, which is 3. Hence, it is sp2. You must understand, this is sp2. Look into this. All these hybridizations are fixed. Now, the issue is, in this, the expected bond angle is 109 degrees 28 minutes. And the real bond angle, The real bond angle remains to be 107. This one, expected bond angle is same, and this also will be 106. Here, the expected bond angle is same, 109 degrees 28 minutes, but actually the real bond angle is 104 degrees 36 minutes. You can see this water, that is what it is. For H2S, it must be 109 degrees 28 minutes, then it is almost equal to 92 degrees. This one is also 120 degrees is the expected bond angle, and it will be angular somewhere around 104 degrees. Angular is the real bond angle. So the hybridization expects these bond angles, real bond angles are these, and I think there is deviation which we need to explain. We have to fix it off. Not only this, I have written some limited number of examples, but I think you have several others also. For example, you see xenon fluoride, right? Xenon fluoride. And this will undergo sp3, this will undergo sp3. sp3, the bond angle must be what? 109 degrees 28 minutes, but actual bond angle is 180. And the shape must be tetrahedral, but it's basically linear. Basically linear. You must understand that, right? So, there is something amiss. There is something amiss. We were going very smoothly with hybridization. We were celebrating that, yes, the flaws which are reported in valence bond theory have been corrected in what? Hybridization. We have been celebrating for some time now. Right, but here is again a pause for you that many of the molecules which are present in chemistry cannot be covered by the concept of hybridization, and now we have to search for another theory. Before we go in for the search for the another theory, what went wrong? What went wrong? Did we ignore something? And the answer is yes. Did we ignore something while proposing hybridization? Yes, the answer is yes. You shouldn't have ignored something. And what is that something? If you wanted to know, observe carefully. We will fix it off. Watch. If I rewrite these compounds, methane, then let us write the number of bond pairs. And we will write off the number of lone pairs. Now, what is a lone pair? Now, first of all, what is a bond pair? What is a lone pair? Bond pair is that which is participated in bonding and is shared by the two atoms. It is nothing but the shared pair. In bond pair, two atoms are contributing, one from the water atom, the other from the other atom, and this shared pair is called the bond pair. You know very well, as the bond is sounding very much, right? But what is a lone pair? A lone pair is a pair of electrons that belongs to the central atom, present in the outermost shell, but does not participate in bonding. So I can simply say a pair that belongs to the valency shell but does not participate in bonding can be called as lone pair. So a pair that belongs to the valency shell but does not participate in bonding can be called as what? Lone pair. How to calculate it? Observe, I will calculate it here. Right, let us take the case of carbon. Let us take the case of carbon. Now you tell me carbon belongs to how many, which group? It belongs to fourth group. So total number of electrons that are present in the valency shell are 4, right? Are 4. So if it is 4, it has invested all the 4 to have an overlap with what? Hydrogens. It invested all the 4. So you will have 4 bond pairs. And when you invest all the 4 pairs in bonding, the number of electrons that are left in the valency shell are 0. So you don't have any lone pairs here, so it is 0 in case of methane. Let us take another example. If you take BCl3 and now the boron belongs to the third group. It belongs to the third group. It belongs to the third group, right? So the total number of electrons present in the valency shell are 3. They are basically 3, right? And you invested all the 3. You see here, you invested all the 3 with chlorines because chlorine atoms are also 3. So you invested everything, nothing is left in the valency shell. So I can simply say you have 3 bond pairs and again 0 lone pairs. 0 lone pairs. And now what I will do, I will take the case of beryllium chloride to you. right, where beryllium is the central atom. Now if you see beryllium, it belongs to the second group. That means the number of valence electrons present in the second shell are 2. You invested all the 2. You invested all the 2. So you will have 2 bond pairs. And again, nothing is left for you. That is nothing but 0. So I continue writing. So if I write PCl5 for you, phosphorus belongs to 5th group. So the total number of electrons present in the valency shell is 5. And you invested all the 5 with chlorines. So again you will have 5 bond pairs. Since you invested everything from the valency shell, you hardly have any electron. So the number of lone pairs remain to be 0. 0. And come again with SF6. SF6. The sulfur belongs to the 6th group. It belongs to 6th group. That means that the total number of electrons that are present in sulfur are 6. And you invested all the 6, right? So the number of bond pairs are 6. And the number of lone pairs again remain to be 0. So if I consider IF7 and interhalogen compounds, IF7, it is IF7. Iodine belongs to 7th group. Halogens, 7th group, right? So you have 7 electrons in your pocket in the valency shell and you invested all the 7 with fluorines. So you have 7 bond pairs and again the lone pairs are 0. Again the lone pairs are 0. So I can continue the list. I can continue the list, right? I can continue the list. And when I continue this list where the bond pairs are fine, but in the list you see, whenever what I say is these molecules are beautifully explained. They are beautifully explained. They are beautifully explained. They are beautifully explained through the concept of hybridization without any flaw. Flawless, beautiful, great explanation by hybridization. So convincing is these molecules. Now, if you ask me, how do you actually remember these molecules so beautifully explained, then I can say, watch here, then I can say the number of lone pair are nothing but towards zeros. When you don't have lone pairs, hybridization is beautiful, great, no equivalence, greatly explained, greatly convincing, beautiful. When you don't have what? Lone pairs. When you don't have lone pairs, you can explain all the molecules, everything. In fact, look into this. If you look into sulfate ion, in the previous session I was telling, look into this. This is beautifully explained by hybridization. Beautiful. Why so beautiful? The number of lone pairs are 0. For example, sulfur belongs to 6th group. So it has total of 6 electrons. It invested everything. See here. 1. In this bond, sulfur has 1, 2, 3, 4, 5, 6. So the number of lone pairs on sulfur is 0. So when you have a radical species molecule, when the lone pairs are absolutely 0, then I think the explanation from the hybridization is beautiful, exotic, greatly convincing, has no equivalence. Wow! All these things you can say with respect to hybridization, provided number of lone pairs on the central atom will be 0. Now what are lone pairs? A pair that belongs to the valency shell but does not participate in bonding. Not every pair is a lone pair. Not every pair is a lone pair. Preferably, it must be presenting onto the valency shell, you must understand. It must be present at the valency shell. Right? You must understand that. Right? I can give you another example. You see here, beautifully explained is this molecule, even the perchlorate ion, ClO4 minus. And if I can write this for you, it will be looking like this. This is perchlorate ion, and you can see here, that is how the chlorine, the molecule is. It is tetrahedral. And chlorine will be undergoing sp3. And the shape is what? Tetrahedral. And the bond angle is 109 degrees 28 minutes. 28 minutes, absolutely everything is fixed. There is no flaw. Beautifully explained. Everything expected in the real bond angle, expected shape in the real shape, all match with one another. Beautifully explained. Why? Because the chlorine belongs to the 7th shell. 7th period. 7th group, sorry. Chlorine belongs to the 7th group. That means that it has 7 electrons in its outermost shell. 7 electrons. Let us count it. 1, 2, 3, 4, 5, 6 and 7. Wow. It has 7 electrons. And the lone pairs are 0. Lone pairs are 0. So if anyone is explaining perchlorate ion, beautifully, exotic, wow, greatly convincing, you can use any synonymous words of this, that will be hybridization, of course. It will be hybridization, of course. So I can actually conclude by telling, if the molecule or a species or a radical or a cation or an anion, right, in which the central atom has 0 lone pairs, then the explanation from the hybridization is absolutely wow. What is wow? Expected bond angle and the real bond angle matches. Expected shape and the real shape matches. When you don't have what? Lone pairs. Now that means that the issue will be arising, the issues will be arising once you have what? Lone pairs. Once you have what? Lone pairs. Then I think the hybridization cannot explain any of the species, radicals, cations, anions, which will be having lone pairs on the central atom. Let me give an example. Watch carefully here. Take ammonia. And I'll write here number of bond pairs. Let us write the number of bond pairs and number of lone pairs. And if I take ammonia, then the nitrogen belongs to 5th group. That means that you have total 5 electrons in your pocket. When you have 5, you invested only 3. See here, you invested only 3 in bonding. Only 3 in bonding. So the number of bond pairs are 3 and 2 are left over on your head. 2 are left over on your head. This is the way. They have not participated in bonding. So nitrogen belongs to 5th group. It has 5 electrons. You invested 3. So 2 electrons are left over. And that I call this to be lone pairs. Then this is one lone pair. So you have one lone pair. So whenever I write ammonia, ammonia looks like this. It looks like this with a lone pair. Now if I count the total number of electrons, 1, 2, 3, 4, 5. So 5 electrons and nitrogen belongs to 5th group. So even though you have 5 electrons, you invested only 3. So 2 are left out. Those I call lone pairs. Come to water. Even pH3 also. Phosphorus belongs to 5th group. So you have 5. So you invested 3. So again you have 3 bond pairs. And you have one lone pair, right? Suppose if you take water, then the oxygen belongs to 6th group. 6th group. So total you have 6 electrons. 6 electrons. But you invested only 2. See here. You invested only 2. You invested only 2. Water looks like this. It has 6 electrons. It belongs to 6th group. But you invested only 2. Here are 2. So you still have 4. So this is a lone pair and this is a lone pair. So the total bond pairs are 2 here and the lone pairs are also 2, right? And I can take another example for you. Another example, if you see XCO3. XCO3 and the structure looks like this. Right, and xenon belongs to 8th group, noble gases. So it has 8 electrons in its outermost shell, total 8. 8. Right? But it has invested how many? Let us check it out. You invested 1 year, 1 year, 1 year, 1 year, 1 year, 1 year. So 1, 2, 3, 4, 5, 6. So that means you're left with a lone pair. So total bond pairs, if you see 1, 2, 3, 4, 5, 6. So I can simply say in XCO3, you have here 6 bond pairs an alone pair, an alone pair. And even I can give you another example, that is sulfur dioxide, or even I can say SO3, and the structure looks like this. Not SO3, SO2. Right? SO2. Now you look into this, the sulfur belongs to 6th group. It has invested only 4. Where are the 4? 1, 2, 3, 4. So you still have 2 electrons. So the sulfur dioxide, if you see, it has 4 bond pairs, and then you have a lone pair, 1 lone pair. So total will be, no, it will be having 4 plus 2, 6. Yes, you have a lone pair. You must understand. So you have 4 bond pairs and what? 1 lone pair. So you are accounting for the 6 electrons for sulfur. Now in all this, if you see, in all this, I think hybridization cannot explain this, and this. It cannot explain. The expected bond angle is different, the real bond angle is different. The expected bond angle is different, the real bond angle is different. So the conclusion what I'm making is as simple as that. The conclusion seems to be absolutely this. Hybridization ignores. I would like to underline this. Hybridization ignores lone pairs in determining it ignores what? Lone pairs in determining shapes, bond angles in molecules. It implies clearly the role of lone pairs completely ignored. You must understand. The role of what? Lone pairs is completely ignored while determining the shape and what? The bond angles of the molecules. Completely ignored. It only considers, so I can simply say, hybridization, according to hybridization, what it says is the shape of the molecules, the shape of what? Molecules exclusively, the shape of the molecules is exclusively determined by bond pairs and not what? Lone pairs. That's what is hybridization telling. That means that you are ignoring lone pairs while determining the shapes of the molecules have costed the hybridization. It only thinks that it is only the bond pairs which are basically what? Involved in determining the shape of the molecule and the bond angle of the molecule. You must understand. So basically what we now finally reconciliate is, it is like this, right? It is like this. So you must understand, it is like this. So from this, what I understand is reconciling both, what we basically understand is, I think the shape of the molecule is influenced. When I say influence, that means I'm speaking of determined, right? The shape of the molecule is influenced by both one, lone pairs, and this is what hybridization ignored, as well as, I would like to underline here, as well as even to the bond pairs. Now that lone pairs as well as bond pairs both will be having a stake in determining the shape of the molecules. In fact, I move forward and say, in fact, not only lone pairs, I can simply say the number of what? Lone pairs, and even, of course, the number of what? Bond pairs. You must understand. So the number of lone pairs as well as the number of bond pairs, it is the number, it is basically the number. It is the number which will determine the shape of the molecule and not exclusively bond pairs. So hybridization very conveniently, very conveniently ignores the lone pair's contribution for the shape, and hence it has flaws. Now what happens is the textbook becomes fat. We were so successfully explaining hybridization because we have seen a severe flaw in valence bond theory. Right now we have taken a theory to explain that flaws of valence bond theory. Now we are ending up with the flaws in what? Hybridization, and then we propose another theory considering even the lone pairs, and after considering it, if it has flaws, then we have to take another theory. That is why the textbook is fat. Let us discuss the theory which will consider both lone pairs as well as what? Bond pairs.